So we're going to look at some data of the maximum height of a tennis ball after several times bouncing on a concrete surface. So here's the height after 0 bounces. It was dropped from 150 centimeters. And then after 1 bounce, it goes back to 80 centimeters. And 2, it goes to 43. So the first question is, which is more approximately for modeling the height after n bounces, a linear function or exponential? Now, as I look here, the decrease, if we take 80 and then subtract 150, so it decreased by 70 centimeters. Then here, if we go 43 minus 80, it decreases by 37. And then 20 minus 43, that decrease is negative 23. So as I'm noticing, this is not a constant decrease. So I'm going to rule out the idea that this is linear. And then what we can do is see if we can model that exponentially. So what we can do is take, let's say, the first y value and divide that by the original. So if we go 80 divided by 150, then we can go, what's 43 divided by 80? And let's say 20 divided by 43. And then once we divide that, that gives us an idea of the decay rate. So 80 divided by 150 is 0.53. And then 43 divided by 80 is 0.537. And then 20 divided by 43 is 0.465. And what we can say here is an exponential function. So this is approximately exponential decay. And what we can say, A, the initial height is 150, and B, we can say is about 0.5. So regulations say that a tennis ball dropped on concrete should bounce back between 53% and 58% of the height from which is dropped. Does a tennis ball meet this requirement? So if you notice, over the first 2 bounces, yes, it bounces back to 53%. So this would be yes over the first 2 bounces. And to show that for the first bounce, what we would do is take 80 and divide it by 150, and we got 0.53. And then for the second bounce, we did 43 divided by 80 and got 0.537. So to write an equation that models the height after n bounces, remember an exponential equation is y equals a times b to the x, where a is your initial height and b is your growth or decay rate or factor. So in this equation, instead of y, we're using h. So our height is, our initial height, A, is 150, times our growth factor is about we'll say 53, so 0.53. And then instead of x, we say n for n bounces. So now, about how many bounces will it take before the rebound height is less than 1 centimeter? Explain. Well, that's a lot of work, and I'm going to show you how to use your calculator to make that easier. So I'm going to put in that function 150 times 0.53 and then to the x power. Then we'll delete that other x. And now we'll go to the table. And remember, the bounce back height here, we just happen to luck out 1 centimeter is around 15 bounces. So this y value gives you about the number of centimeters. So here 150, 79. And then to get back to it's about 1 centimeter, we see that here this is about 1. It's around 7 or 8 bounces where it goes back to just 1 centimeter. And we use the table. You could also, after using the table, find the graph. So you could go, all right, well, 150 times 0.53, or instead of using the graph, plug the 7 into the equation to the 7th. So 150 times 0.53 to the 7th is about 1.76. So it'd be around the 8th value.